Hanchen. Last year, together with my colleagues from tolerance management and also with the support of DCS, we tried to work on the topic and the modeling approach for elastic tolerance simulation of the body-in-white Hanchen parts. And it was a really nice experience. And also, I'm very glad to hear to introduce this topic. So, in this presentation, I will introduce 5 parts. The first part is an overview of the current problems we have for the tolerance analysis and during the manufacturing processes, which is also the motivation to initiate this research work. And in the second part, there is a comparison of the existing approaches for the tolerance simulation in the automotive industry. So then I will introduce the concept to address our problems, which is here the elastic tolerance simulation. After then, I will introduce the application of these concepts in the industrial scenario studies, including the modeling procedure and the comparison of the simulation results with the real measurement data. So finally, there will be conclusions and outlook. Okay, so let's start the first part. So the tolerance analysis becomes more and more important in the automotive industry nowadays. It is used to analyze the manufacturability of the complex assemblies in an early stage to reduce the product development time and the cost for the hardware prototypes. So regarding the body-in-white Hanchen parts, like the fender or the door, the bonnet, and the trunk lid, usually the rigid tolerance simulation is implemented to calculate the tolerance startups in the assembly process. However, the rigid tolerance simulation approach has a shortage in fitting to the reality because all the parts in the simulation system are assumed to be rigid, and the influence of the manufacturing processes on the assembly deviation is not considered in the simulation model. So now, by introducing the FEM simulation, we have the possibility to involve the elastic deformation in the tolerance simulation model, but a proper modeling approach still needs to be worked out and validated, especially for the real engineering parts with complicated geometries. Therefore, in this work, I will introduce an approach to build up an elastic tolerance simulation model with 3DCS, and also a comparison of the simulation results with the measurement data. So, as the state of the art, here is a comparison between 3 existing approaches that is popular and applied in the automotive industry to simulate the tolerance behavior. First, we have the FEM simulation approach for the nominal condition or some extreme conditions. With this approach, the user is capable to simulate the flexible parts, and we can obtain the simulation results for every mesh node and element. However, the modeling process and also the calculation process of FEM can be very time consuming, especially when we're dealing with some very large models or the models with very complex and complicated geometries. Maybe sometimes it will take like days to get a single result. And also the part tolerances are usually not considered because we only change the boundary conditions. We don't consider the tolerance distributions of the parts. So besides, we also have the rigid tolerance simulation, which has a relatively simple and fast modeling process. But as mentioned before, the simulation results does not fit to the reality when dealing with the compliant parts and also consider the manufacturing processes. So now we also have another option, which is elastic tolerance simulation. And with elastic tolerance simulation, we are also able to simulate the flexible parts like in the FEM simulation, and the whole tolerance range and also the tolerance distribution of parts can be considered in the simulation model. But since we are talking about the elastic, therefore only the linear elastic effect is considered in the simulation model. So from the comparison, we can see that the elastic tolerance simulation approach seems to have the advantages of both FEM simulation and the statistical tolerance simulation. And that's also the reason we are using this. We are trying to using this method to solve our engineering problems. Okay, now I would like to introduce the concept to create the elastic tolerance simulation model. In order to create the elastic tolerance simulation model, we should first build up a rigid tolerance simulation model. The modeling process, I think it is quite familiar to most of us. We're starting from the CAD geometry. We can export it from the data bank and using a DCS converter to convert different format of geometries to the format that can be processed by DCS. And then we integrate all the necessary informations like the points and the tolerance and data and also the measurement strategy into the simulation model so that we can get a point-based rigid tolerance simulation model. So based on this model, we can start our process for the elastic tolerance simulation model. We need to link the FEM information to the rigid model so that all the parts, all the compliant parts in the simulation system becomes deformable. And then we need to define the compliant moves according to the manufacturing processes so that we get an elastic tolerance simulation model. And this simulation model can be used for different scenario studies. So as we see here, there are two important steps to build up the elastic tolerance simulation model, which are here, to link the FEM information and to determine the compliant moves. Therefore, I would like to introduce a little bit more detail about these two steps with the example of an fender assembly, which is simulated in this work. So the first important step is to link the FEM information. I assume that we already have the rigid tolerance simulation model with all the necessary DCS points defined in the model. Then we will need to import the FE measures for every single part in the model together with the corresponding material information into DCS. Then 3DCS will automatically search for the nearest FE node from this DCS point and create a group of these nodes. In the end, the 3DCS will generate a new mesh file with a group of this DCS node and an extra reduced stiffness matrix file where the stiffness information of this corresponding to this DCS point will be recorded. And these informations will be used for the creation of the elastic tolerance simulation model. So the second important step here is to determine the compliant moves. As we see here, for the fender body white system in this work, it consists of the body white and the fixtures and also the fender assembly. So for the fender assembly itself, it consists of 4 single parts: the panel A, the support part B, and a reinforcement part C, and another support part D. So all these single parts will be joined together by following a specific joining sequence. As we see here, the part B, the support part B, will be clinched on the panel A to form the sub-assembly, let's say AB, and then the reinforcement part C will be again clinched on the sub-assembly, and finally the support part D will be joined with the sub-assembly through the roller hemming process. So DCS provides different types of compliant moves to simulate different types of manufacturing operations. And in this work, I assume that two parts are firmly joined together after the joining operation, and no relative sliding occurs between parts, because as we know, in the roller hemming process, there will be some adhesive material between the parts, and during the roller hemming process, these two parts may be slide relative to each other, and this nonlinear behavior will not be considered in this model. So with this assumption, I use the joining move to simulate the effect of the clinching process as well as the roller hemming process. For the roller hemming process, I define several points along this hemming edge and use the joining move to combine the support part D and the panel A, and like they are firmly connected together after the hemming process. So I use the clamp move to simulate the fixture closing or releasing process by constraining the specific degrees of freedom according to different types of the fixture. Okay, now we have a general understanding of how to build up an elastic tolerance simulation model and some important setups, so to say, in the simulation model specifically for this work. I would like to introduce the application of this concept in the industrial scenarios. I will starting with the modeling procedure and then show the comparison between the simulation and the measurement. So first we have a CAD geometry and import it to DCS, and then we integrate the necessary points, which are here the fixture points, the measurement points, the contact points, and I've also used some extra points to create a better visualization of the results, but this won't have any effect on the simulation result. Then I define the tolerance according to the tolerance specification and for every single part, so that I get a rigid tolerance simulation model. But we want to create an elastic tolerance simulation model. Therefore, I link the FEM process following the steps I mentioned before, and also I define a list of assembly sequence, or here the joining sequence, by using the compliant moves, so that finally I get the elastic tolerance simulation model for the fender. And this model is used for two different scenario studies. Okay, now I'm going to show this the description of these two scenarios. So in the first scenario, the fender assembly is clamped on a measurement frame after the joining operations at this fixture position. And in the second scenario, the assembly is bolted also on a measurement frame, but at the same positions as it is on the body wide. So in the real assembly process, the best fit method is used to put the fender on a proper position before mounting it to the body wide. So in this best fit process, the gap and the flashiness in Y direction will be first adjusted, which means the gap and flashiness between the fender and the bonnet. And then the position of the fender will be adjusted in the Z direction, so that the fender fits to the longitudinal beam of body wide. And finally, the gap and the flashiness between the fender and the front door, which means in X direction, will be adjusted. Therefore, a deviation in X direction of the fender assembly is usually observed, especially in the bottom area, and this deviation may lead to a deformation in the front area. So in order to verify this phenomenon, I defined a deviation of 2 millimeters in both simulation scenarios. It's like a kind of worst case. So, and I define the measurement point in the front corner here to verify the phenomenon, and also as the comparison of the simulation and the measurement. Okay, so now we have these two scenarios, and let's take a look at the simulation result first. So in this picture, we can see the simulation results which I exported from DCS. This is the result for the MPY, which means the measurement point in Y direction. It's located here in the front area, as we see in the picture, the blue spot. So we can get a histogram of how the assembly deviation looks like, and we get some statistical results like here. I from 3,000 simulation runs, and by considering the compliance moves and the deviation I given to the system, and also the tolerance, we will have a mean value of minus 2.82 millimeter in Y direction. So I'm using the car coordinates. So minus Y direction means normal to the surface, normal to the outer surface of the part. Besides, we also get the other statistical results like the standard deviation or 6 sigma and the estimated range, and also a list of sensitivity analysis. So in this case, we see that in the first place, the tolerance that affect the assembly deviation in the first place is the tolerance of the fixture here, from the fixture here. It locates here. It makes sense because this position is actually also quite close to the measurement point, and also there are many other tolerances that are making a difference, but it seems that the fixture tolerance here makes the most contribution. So this is how the simulation result looks like, and now I would like to go back to the slide and show the measurement result. So here we see the measurement result. In the pictures on the left, we see the fender assembly on a measurement frame with here all the fixtures around it. And in the first scenario, all these fixtures will be closed, and we put some shims at this bottom area to create this 2 millimeter deviation and observe the deformation in the front. In the second case, as I said, the fender assembly will be bolted also on this measurement frame, but like the same condition, the same positions as on budding white. And also we will measure the deformation in the front area. And when we look at the measurement result, we see here displacement at x9. It means like the displacement in the bottom area. We see here the value here is not exactly 2 millimeter in x direction, because we are using some shims and creating this deviation like manually. So it is very difficult to ensure an exact value of 2 millimeter and without any deviation in other direction. But even though we see the phenomenon that a relatively large deformation is observed in the front area on the measurement point in Y direction, and also in the second scenario, when we apply this 2 millimeter deviation, we see a deformation of minus 3.24 millimeter in Y direction. This is so what we observed in the measurement. When we look at the simulation result again, so on the right side, there's two very nice colorful pictures I view, and it is also created by from DCS, from 3DCS. And from the picture, we can clearly see that the deformation tendons of from the simulation result is consistent with the real measurement that when I apply a deviation in the bottom area of the fender assembly, we see a relatively large deformation occurs in the front in both cases. So if we look at the result, here I compare the deformation of the measurement part with the mean value and also considering the deviation range. Here in the first scenario, we see that the deformation is actually quite close to the mean value. And also, of course, within the deviation range based on this mean value. And in the second scenario, the deviation here is a little bit away from the mean value, but still it is within the deviation range relative to this mean value. It means that by using this concept of elastic tolerance simulation, we get the same deformation tendency of from the simulation, and this tendency is consistent with the reality. And also, when we look at the numbers, it is not exactly the same, but also quite close. Of course, it would be much better if we can measure like several samples or even hundreds of samples to create a very good, very nice distribution and compare the distribution directly. But this work is like the first step to implement the elastic tolerance simulation for the real engineering scenarios. Also to say the first step to bring the elastic tolerance simulation concept to this kind of complex geometry and real engineering problem. I would say, and this result is actually a very good start. So finally, we come to conclusions and a brief outlook. An approach is developed to implement the elastic tolerance simulation for compliant assembly and considering the manufacturing processes. And the proposed modeling approach is applied in an industrial scenario, as we see here, the fender assembly, and validated by real measurement data. So as an outlook, in the future, an automatic integration process of the points from CAD model to the simulation system may be developed, and it can definitely speed up the modeling process. And a simulation system containing more compliant parts can be created, which so that we can get a more realistic results. And also maybe the nonlinear effects of the clinching and hemming process can be integrated in the simulation model, which improves the simulation accuracy again.